I'm a researcher at Sandia National Labs, and I'm very excited to be presenting here at the NICE meeting virtually. And today I want to talk about something a little bit new. It's a new effort that we've been doing at Sandia and across a number of collaborating institutions over the last few years, or last few months, say. It was a recently funded project out of the Department of Energy Office of Science. So it's called COINFLIPS, and I'll explain what the acronym stands for and why we're talking about probabilistic neuromorphic computing in a few minutes. But I want to kind of set the context with a recent paper that we came out with. It was published in Nature Electronics about a month ago. The first authors here, Darby Smith, I'm showing. And the paper focused on how neuromorphic computing is advantageous. We showed that neuromorphic computing is advantageous for Monte Carlo random walk calculations. And this is not necessarily a machine learning algorithm. This is a probabilistic applied math algorithm. And there's several things I think are very exciting about this line of research and this approach. It kind of broadens the impact of neuromorphic as a whole. And I'll walk through briefly what we found and how that sets us up for the future. So in this study, and I talked about this at NICE last year in more detail, if you want to go back and look at that talk, we designed a neuromorphic algorithm that roughly looks like this. We configured spiking, leaking, integrate, and fire neurons into small little circuits that count the number of spikes coming into those mesh points, and configured a mesh out of those little counter nodes that could map to whatever computational graph you might care about. In the case of numerical computing, that might be a meshed description of some physical system. In graph analytics, it might be mesh point for each node of a graph. In neural networks, there might, or in machine learning, it might be some like a graph neural or whatever. And the idea is that you could do random walks over this mesh simply by passing spikes back and forth. And what you can see here is an example of heat diffusion or Brownian motion over the surface of a torus. The algorithm, in effect looks something like this. Each mesh point gathers a set of spikes coming in from all of its connections, and then probabilistically divvies them out to the whatever neighbors according to the Markov transition probabilities that describe the physical problem you care about. And in effect, what you end up doing is you calculate an evolving probability distribution of the states of that system. Now, there's a whole story about how this is advantageous for a large set of partial differential equations and financial applications and biological applications and so forth. I won't go into that, but I will say that we did see that Loihi and True North and Spinnaker as well, when we examined Spinnaker also, are computationally advantageous on this by this definition we show here, which is that even on these sort of early generation systems, we see an explicit power advantage, which is not surprising given it's neuromorphic, on the number of Walker updates per joule. So this is an energy advantage, not a power advantage, it's an energy advantage, which says that, even if I were to speed this up, I'm still doing it at better energy, energy per calculation. And the counterbalance is, well, wouldn't this be slower? And it is, in fact, a little bit slower than a parallel conventional system like a GPU or multi-core CPU. However, what we see is that as we increase the complexity of the problems and the number of random walkers, which is often the limiting factor, the neuromorphic solution seems to be speeding up. And it's just the nature of how we parallelize it. And the conventional system does not. It's embarrassingly parallel, but it also means that if you want to speed it up, you have to add more resources to it. So stepping back, where does this advantage come from? And as I mentioned, this has to do with the high degree of parallelism of the neuromorphic hardware being a really nice fit with the embarrassingly parallel structure of these Monte Carlo random walks, these sort of random, these stochastic processes over a Markov chain. And this is a nice example of something that shows up in a lot of computation where you have a choice, where you can do a single very large complex calculation, or you could perhaps represent that same problem as a lot of simple calculations that you can do in parallel. Now, neuromorphic is going to thrive on the simple calculations in parallel. compared to the large arithmetic heavy complex calculation. But often those simple calculations depend on stochastic sampling or some probabilistic component, whereas the single computation is deterministic, or very often. And so we think that to take this type of finding and scale it into the future, that the probabilistic component of this algorithm will likely be a limiting factor. And it's limiting in two ways. One is the quality of the random numbers that we're producing. In other words, kind of the bit precision of it, the fact that they're uniform random numbers as opposed to some particular distribution that we might want. And then also the quantity and location of the random number generation. These chips are fantastic. They have highly parallelized random number generators, but the number of random number generators is an order of magnitude smaller than the number of neurons or synapses on these chips, because that's, of course, not what they've been emphasized to do. So we're still serializing the pseudo-random number generation in most of these cases. So what happens if we were to build a neuromorphic chip centered on probabilistic computing? Now, this is not necessarily a novel idea. Something that actually comes up at NICE probably in a few talks every year. When people talk about what is brain inspiration, we have talk, people go, it's analog, it's spiking, there's high degree of connectivity, it's learning. And of course, the brain does all of these things, and we kind of want our neuromorphic systems to do all of these things. But stochasticity is fundamental to how the brain functions as well. And there are some very nice examples from Wolfgang Moss's lab and others of showing how stochasticity in neural algorithms can be very powerful. Now, if you look into the brain at where stochasticity really is occurring biophysically, the obvious dominant source, if you were to ask a neuroscientist, is at the synapses, not really at the neurons, which is where it tends to be emphasized on neuromorphic hardware. So at each synapse within the brain, during a spike being transmitted down the axon, there's a release probability of whether or not the synapse itself will communicate to the downstream target by basically having a coin flip of sorts of whether or not the synaptic vesicle will hit the cleft and dump neurotransmitter into the dendrite, to the dendritic spine downstream. Now, this is a highly regulated process. This isn't just, this is how it has to be. The brain seems to be dynamically tuning these release probabilities over time. This is what short-term plasticity really is in terms of short-term facilitation and depression. And also, it's genetically encoded. Different neurons have different baseline release probabilities. Mossy terminals in the CA3 have very low release probabilities, but if there's a burst, the release probabilities go up, for instance, and that's unique to that synapse type. So that's at the synapse level. What about at the functional level? And I think I mentioned this paper a few years ago at NICE, but I think it's telling because people are now beginning to see that when you record from hundreds or thousands of neurons in the brain using these large-scale imaging techniques that are available now, we're starting to see sort of stochastic sampling occurring at a population level. So the brain appears to do this at a device level, kind of the synapse level, as well as at the algorithmic level. And this is a case where in the CA1, where we see place cells during both kind of exploration of an environment as well as in what we would call replay, that the replay events appear to actually be a Brownian motion kind of random walk sampling, not all that different than what we showed in the Nature Electronics paper a few weeks ago. So how is the brain using this ubiquitous stochasticity? I mean, the stochasticity is everywhere within the brain, and it's not kind of an artifact. It's not random. It appears to be used. Well, it's unlikely that the brain is actually doing what we showed in that paper. The algorithm we showed was, very simple in some respect. Each spike is a stochastic process sampling some model. That's unlikely the case. At the same time, the sort of canonical view, I'd say, or the simple view, that kind of a convenient view that exists in the neuroscience community, where all of those random events are just averaged over because there's so many of them and they're all happening at the same time, and it's just some expected value being calculated. That's almost certainly not happening either. The brain seems to be using the stochasticity to do something of relevance and importance. So I'm not going to be able to answer this question. I think this is a big open question that the field as a whole has to think about and address going forward. But I think from a computing point of view, we can say, well, what can we do if we were to take this sort of approach where we have stochasticity as a easy to access resource on par with having memory and computation as resources that we worry about. So many applications of computing have inherent fundamental uncertainty in them. This is a bistable image is kind of, you see it all the time in cognitive science studies where humans will look at this and they'll say, well, this is two things at the same time. In fact, there's a distribution of things that when you look at this, is a distribution of things that this is. AI algorithms, on the other hand, if I were to take a computer vision algorithm, it's not going to do that. It's going to give an answer. It'll probably say it's a vase. But it's not going to say it's a vase or it's faces, but it's not both at the same time. It's one or the other. And now that's, AI, where, clearly there's a need for probabilistic interpretations of what's going on. But we also see this in everything from climate modeling and weather forecasting to things like particle physics, where the underlying physics that we're modeling and trying to understand is probabilistic in nature. So if we were to have a vision here where we want to build a computer that has stochasticity at the rate of which the brain has stochasticity, which we, back of the envelope would say it's 1 billion random numbers per microsecond. And we want to target these sort of computing and AI applications. We really want to take the best of a couple of worlds. We want to take what we know out of neuromorphic computing, a neuromorphic architecture approach, but couple that with these stochastic devices that could potentially provide us stochasticity at that scale. So one approach is simply to take what we're doing today in neuromorphic computing and kind of building up spiking systems and adding analog to that and doing more sophisticated algorithms. And now we kind of butter on top of that a stochasticity layer. And I think there's value in doing that. And I think we should continue to do that. But the problem with that is that if we're adding stochasticity in at kind of the top layer, where it's like through a pseudo-random number generator on top, we're not really gaining the advantage of having cheap stochasticity that devices might provide us at the lowest level. And this is one of these awkward things where if we eliminate noise at the device level only to add it later, it's inefficiency, it costs power, it's expensive. On the other hand, if we were to build our chips kind of central to the idea that our devices are noisy, and we're going to accept that noise and use that noise to our advantage, and then on top of that, layer circuit and architecture concepts from things like spiking hardware, then we potentially could gain some nice advantages in terms of computational efficiency. So this is kind of a hypothesis. This is, I don't know which is actually the best approach, but I think it's worth exploring a little bit what's on the right. So that's where the COINFLIPS project comes in. We had this project, it was granted by the DOE Office of Science. There's a fairly large program looking at co-design strategies for novel microelectronics technologies. There are 10 or so projects were awarded from across the country, different Department of Energy labs. And our project is really focused on taking what we would say is a true co-design approach. So blending new algorithms with novel devices and materials and new physics and new circuits, and taking this brain inspiration I talked about before. And we're looking across devices, circuits, algorithms, and this sort of probabilistic application space. And in doing that, and we're collaborating with a number of people at NYU, University of Texas, Austin, Oak Ridge National Labs, University of Tennessee, and Temple University to approach how a system like this might look. And it's a 3-year project. It's a nice amount of money, but it's not an enormous amount of money. And so we're not trying to build this chip, obviously. What we're trying to do is show kind of a sense of proof of concept that advancing all of these kind of scales of microelectronics in parallel would allow us to have a proof of concept sort of understanding of what a technology like this might look like going forward, and is that worth doing? So I'm going to just jump through relatively quickly in the remaining 10 minutes of the talk at the different scales of what we're looking at. I'll spend probably the most time on the algorithms and theory because that's more my background, but there's a lot going on at each of these scales. So I'm going to start with the devices just to give you a flavor of what we're looking at. So the goal when we look at a COINFLIPS device is we really want a device that basically is like a weighted coin flip, where basically I could say, here's a 50-50 coin, a 0 or 1 with no bias at all in what comes up. Or perhaps I want a 20/80 coin where it's going to be tails 80% of the time and heads 20% of the time. And if I can control that and tune that, I have a nice resource there at a very, very small scale. So information encoded in the probability, that the Bernoulli probability that my device is at a certain state. Now we can do this. There are devices that have this sort of stochastic switching that, you can think of some probability of switching to heads and some probability of switching to tails, and there's a difference in those two probabilities. And so you get some tuned you can tune that and you get some bias towards more likely to be in tails than heads, for instance. There are two types of devices we're looking at, and I'm not going to go into a ton of detail on either of them, but we're looking at magnetic tunnel junctions, and we had a lightning talk yesterday about some of the devices that Janan Corvia is looking at UT Austin and others, and she's collaborating also with the folks at UT Dallas. And then Andy Kent at NYU is also looking at magnetic tunnel junctions, also a different variant of those that have a different types of tuning. And then within Sandia, we're looking at what are known as tunnel diodes, where they can be very specific about some of the impurities that they put within the devices in order to control this tunability. I'm not going to talk more about the devices. Maybe in future talks we'll go into detail on those. But I want to switch to the other side now, which is more on the application side, about where we think a COINFLIPS-like system might be able to have real-world impact on a sort of a science application. So with our colleagues at Temple, we're looking at a basic, very straightforward, kind of state-of-the-art physics, particle physics application, where you might be colliding an electron with a proton or some sort of nucleus of an atom, and you watch what scatters off when that collision happens. And this is motivated by the collider up at Brookhaven, but it would apply to probably a lot of these different systems, where you see when there's a collision event, there's this scattering of subatomic particles, which are measured by various sets of arrays of sensors. And you see what the data that comes off looks along the lines of what you see at the bottom here, where you have this sort of what looks like an image, but they're kind of a collection of a number of events at each of these voxels, kind of radially out from where the beam is traveling. And part of the big challenge they want to understand is, what are these things that they're observing off on the side events of interest, or are they just noise? They're called jets. Now, this is a stochastic problem, the stochastic AI problem. We see this jet, we want to identify, is it something that is of interest? And if it's of interest, we want to very quickly, I'm saying within a few nanoseconds, signal to a detector that's much slower and maybe much more elaborate to start collecting as much data as possible. But you don't want to do that if it's not an event of interest. So you have to train this model to say, is this thing I observed something relevant? It's of course a stochastic thing you observe, and the physics are underlying that we care about are themselves stochastic. So they constrain these models by doing lots and lots of Monte Carlo simulations, on supercomputers, in a sense offline, that basically are doing some sort of stochastic model of what that physics that they expect to see is. So we believe that the COINFLIPS-like neuromorphic approach could have the advantage of either accelerating this Monte Carlo simulation or accelerating this AI application. So I'm going to now jump to sort of the algorithms of where we might see those things being impacted. Now, what I'm going to show here is pretty much early thoughts on these topics. And since these are kind of straw man approaches that we'll obviously be improving on, but the idea is that we think moving in this direction is going to have a lot of value. So today, when we want to do, so first I'm going to think about the sampling, the numerical computing task. Today, when we sample uniform numbers to create arbitrary distributions, basically we're taking pseudo-random numbers that are kind of uniform ones and zeros. And this is what everyone does. And there's a lot of knowledge going back to the beginning of computing of how to go from a uniform random number to some distribution I care about. Now, these distributions are often very weird and wonky, so this sort of conversion might be expensive. So one of the things people do is they say, well, what if I have a true random number generator, some sort of biased source? It could be anything from some device that has noise to a lava lamp or whatever. And there's a way you can go from that to uniform random numbers. On the other hand, and while it's been explored, this is of course more expensive because I'm kind of adding a step to it. On the other hand, what if I could just go from these biased random numbers straight to the distribution I care about? These might be relatively cheap to build. This is what I want. But of course, no one's really thought about how to do that because there's really no need to. Why would you ever do that if you're doing it in software, which is what we generally do over here? So just kind of restate what I said. Today, we pull a random number from some, we need to have a random number that matches some physics distribution. So we use a pseudo-random number, and then we convert that to the desired target. And that can be expensive. So is it possible to just directly create a random number that is sampled from some distribution that looks like this? You know, this would be like a mixture of a Gaussian and an exponential, let's say. But who knows? It could be anything. So one way is just to break this distribution down into kind of a binary tree of sorts, that the first coin represents the first bit, which would be is on the left or the right half, the left or the right half of this PDF. The second coin would be the second bit, which says, okay, now I'm in this quadrant versus this quadrant, or this quadrant versus this quadrant, and so forth. Like a walk down the tree and do this. Now, this works, and there's no reason you can't do that. And if you have a coin that you can continuously change the, dynamically tune the weights, you could just build a coin that does this and produces a random number like this. But if you have a coin for every coin flip here, that could be an exponentially large number of coins. On the other hand, we can actually, you can see that there's some commonalities, there's some structure in this sort of tree. And I only need one coin for this layer, for instance. And this layer here, I can make this a conditional, where this coin has a probability as a function of what happened with the first flip. So this sort of insight lets us think that we could actually probably build a neuromorphic-like approach, because neurons are good at looking at correlations, and they're good at looking at redundancies. And so we could have a resource of coins that are flipping at whatever probabilities we've either put in them or just randomly, and have some neural layer that actually assembles those coins into the sort of binary random number that I care about. And we've done some preliminary studies on this sort of idea. This is a very trivial example where we're fitting this orange distribution, and we can see that the COINFLIPS actually do a pretty good job of that. So I'm going to quickly, in the last couple of minutes, just show a very quick illustration of what we might want to do with AI. So one of the, just to skip forward, it's like, what does it mean by sampling synapses as opposed to sampling neurons? So one thought is we could take, and this is again a very trivial example, but it's something that is illustrative of what we could do, is we could actually think about what it means to sample the weights of a neural network. So this is a very simple MNIST network. You train it up, it's 2 layers. It classifies things, it does it fairly well, but all the weights here are constrained between 0 and 1, and they're analog of sorts. They're continuous value between 0 and 1. Well, I can treat those weights now as a sample probability. So each weight now is actually 1 or 0, but it happens at a probability that is equivalent to what the trained weight is in the previous example. And when I do that and I sample this network now thousands of times, I actually will get a distribution coming off the back end that says, okay, this number here, it's not a 4, it's not a 7, it's some probability of being a 4 or 7. And when you do this, you actually see that it works pretty well. And these are the sort of failures, and this is what tells us the most. And you can see that, okay, this one here, it said it was a 4 36% of the time, a 7 35% of the time. 7 is the right number, the right label within MNIST, but I can't tell you what this is actually supposed to be. Some of these are easier than others, but you can see how this might be considered a 0, a bad 0, or it's a 6, for instance. What's nice about this approach is that it is robust to noise. You can go down to fairly low quality stochastic bits. In this case, it's 6 bits. We're still getting basically the same answers. So just like with the analog weights, by having the information not represented in the analog weight, but now it's an analog probability, we can go down to fairly low precision, and it holds up pretty well. So this is all in simulation. Of course, we don't have devices doing this yet, but I think that this is something that we easily, the dumbest way possible, just having our devices in a linear algebra sort of setup, we probably could get it to work. So finally, the question is, now, these algorithm approaches were kind of the direct way of doing it, could we do some sort of AI enhanced co-design across scales? Ultimately, we want to build circuits and systems that are able to map our devices to these algorithms. And now we can do it using kind of well understood principles, like I mentioned, using crossbars of weights of devices that do sampling. But the other thing we might be able to do is use evolutionary approaches, reinforcement learning, things like Katie Schumann has published eons, for instance. And the idea would be that taking advantage of AI and machine learning, we might be able to sort of more gracefully and naturally fit the sort of particular requirements we'd have on the algorithms with the particular features and properties of the devices we're looking at. So this work is being led by Suma Cardwell at Sandia, working with Katie, as well as with the device people like Jinan and Andy and Shashank. So just to kind of wrap up, we see this as a future computing paradigm. This is kind of one potential next opportunity beyond neuromorphic or neuromorphic plus noise. So this is something we'd love to work with anyone and everyone on. We're trying to understand what the opportunity space looks like here. This is early days on this sort of thinking. But with that, I just want to thank the broad COINFLIPS team who I'm working with, and especially thank Office of Science and particularly Oscar and BES for supporting this research. Thank you very much.